Next, we're going to take a look at our first example involving more than one variable and a constraint equation. So I alluded to the fact that certain optimization problems might have more than one variable when I first introduced optimization problems, and next we're going to take a look at our first example. So this example we want to construct a cylindrical can. So the goal, so our objective, is to construct a cylindrical can or a cylindrical container with a fixed amount of material. And we want the container to be as large as possible. So what is the maximum volume of a cylinder constructed using only a fixed amount of surface area A. So we have so much material, like say metal. We have so many square inches of metal, and we want to, we can, cut it and piece it however we want, and then we want to take that metal and form it into a cylindrical can. So basically the total surface area of the can is going to be fixed to some constant, which we'll call A. Now there's two ways to go about this problem, or the two ways in which a problem like this might be given. The way I'm going to do is using A as a parameter, or a constant. So A is going to be viewed as a constant throughout the problem. So it's a fixed problem parameter, A. So we regard it as though it's a known constant, and in the end, the formulas that we uncover will depend on this parameter A. So we treat A as a constant throughout, and then our final formula for the maximum volume will depend on A. This way we're solving an infinite number of problems with one stroke. So instead of just saying, okay, I have 100 square inches of aluminum material, what's the maximum size volume cylindrical can I can make out of that? Well, okay, you do the problem using a total fixed amount of 100. Then somebody else comes along and says, well, I have 200 square inches, and somebody else has 175 square inches, and so forth and so forth. So you would find yourself solving the same problem, 100 different times if you have 100 different values of A. So instead of doing that, and this is a very common methodology or technique used in engineering, is we solve the problem once, treating A as a constant, and A is called a parameter. So it looks like a variable, but it's treated as a constant. We just don't know we haven't decided on which constant it is. Is it going to be 100 square inches or 150 square inches? We're not committing to any particular value, but we know that it is some constant value. And we're going to proceed just calling it A instead of, and then what we end up with is a bunch of formulas that will depend on A, and that's kind of cool because somebody says, oh, here's 100 square inches of aluminum. Plug 100 into your formula for A, and here's the maximum volume. Somebody else, 142 square inches. Plug 142 in for A, there's the maximum volume. So we're solving a whole class of similar problems simultaneously by doing that. So basically, our constraint is that A is fixed, and then we want to maximize the volume V. So our can is going to look something like this. Something like that. And then let's draw some sides. So more or less like this. Okay, the bottom is a little off, but you get the idea. Okay, so there's the can. So we have a cylindrical can, and the radius of the base is r, and then the height is h. So those are our two variables that we are assigning, r and h, the radius of the base and the height. Okay, so we need to come up with some formulas. So first of all, the volume of a can is just equal, or volume of a cylinder is just equal to the area of the base and then times the height, because we have this area down here, we multiply it by the height, and so the area of the base is pi r squared h. So we're trying to maximize this function. We want to maximize v of r and h. Now we have two variables, so there has to be something else. There has to be a constraint. And our constraint is that the total surface area of the cylinder is fixed. So our constraint is that the total area is this fixed constant. So A is a constant. And then what is the surface area of a can? Well, we have surface area of the top, surface area of the bottom. So each of these comes in with pi r squared. So I get pi r squared plus pi r squared. That's 2 pi r squared. So that's the area of the top and the bottom of the can. And then we get plus the area of the sides of the can. Now the area of the side of the can, it's simple to remember. It's just the circumference of the base times the height, right? So you can imagine if you have a paper cylinder like this, taking scissors and cutting vertically along the edge, and then taking that and then flattening it out. Well, the length of that strip is going to equal just the circumference around the base, which is 2 pi r. And then the width of the paper is just going to equal h. So it's 2 pi r h, the circumference of the base times the height. So just think of it like a rectangular strip of paper, then fold it around. It's just going to be the circumference of the circle times the height. So this is our constraint equation. Now with these sorts of optimization problems, we want to use the constraint to eliminate one of the variables. Now we have a choice. Do we eliminate r or do we eliminate h? So you can go about this either way. For this problem, I advise eliminate, let me think about this, eliminate r. So the idea is, which variable is it easiest to solve for? Is it easier to solve for h, or is it easier to solve for r? Well, if we want to solve this for r, and remember a is a constant, it's just like pi, if you will, except we just don't know what the value of a is, but a is a constant. So if we want to solve this for r, we're going to have to use the quadratic equation, because we have an r squared term, an r squared, and a constant term. So then we get a quadratic equation where r is some function of h, and it utilizes a quadratic equation. That's not very pretty. However, h is all by itself in just a single term, so it's not too difficult to solve for h. So to solve for h, let's put the work down here, I'm going to subtract 2 pi r squared from both sides and then divide by 2 pi r. So we get a minus 2 pi r squared is equal to 2 pi r h. I basically moved the 2 pi r squared to the left-hand side. Okay, now I'm going to divide out by the coefficient of h, 2 pi r. So I have a over 2 pi r minus 2 pi r squared divided by 2 pi r. That's minus r. 2 pi r squared divided by 2 pi r is just equal to r. So h is going to equal a over 2 pi r minus r. Now this represents the following. Given a radius, this is the corresponding value of the height of the cylinder or this is a corresponding value for height that you have to have in order to satisfy the constraint that the total surface area is equal to a. So as long as you follow this, given an r, here's what the h value is, and that will satisfy the total surface area is equal to a. So the idea is we take this value of h and we insert it into our equation for volume. So let's clear some space here. So since we've used the constraint to derive this equation, let me just pick this and slide this up here. Pretty cool. And then let's also clear this stuff from down here. Okay, so Therefore, the volume as a function of r alone is going to equal pi r squared times h. Well, h is equal to a over 2 pi r minus r. So the volume equation, pi over pi cancels, r squared over r is just r. So we get a r over 2 minus pi r cubed. So that is the equation for the volume solely as a function of the radius. And notice that our parameter a shows up in this equation. So if you're working with 100 square inches of sheet metal, a would equal 100, and this is the formula for the volume. So once you fix r, this is the volume of your can. Right? So if r is equal to 3 centimeters, you use this formula to give you the volume. And what you're actually doing is h has already been computed using the constraint that the total surface area is equal to 100. So h is already given in terms of the radius and the surface area. And then we use that in the volume equation to come up with this equation. So now this equation only depends on the parameter r. Now, this is going to have some boundary points. So certainly r equals 0 is a boundary point, right? So you cannot have a cylinder with radius less than 0. So one physical limitation on the values of r is r is equal to 0. Now there's another one, and we can, I suppose I don't even need this stuff anymore either. So we can think about factoring out an r times a over 2 minus pi r squared. So the other 0 of this equation, well, there's 3 zeros, but then if we set this equal to 0, a over 2 pi, so r is equal to the square root of a over 2 pi. So that's another boundary point. And in fact, since you're taking the square root, it's going to be plus or minus. So if I set this equal to 0 and solve for r, I get plus or minus a over 2 pi. Now we're not worried about the negative root because that's a negative value of r, which we rule out based on physical reasons. So basically, this is a cubic function, and it's going to look like this. Right, so here's r is equal to 0, and here's the volume as a function of r. This is going to be the negative square root of a over 2 pi right here, and that's positive square root of a over 2 pi. So for positive r, this function's only positive between 0 and the square root of a over 2 pi. So the domain of this function is going to be r is contained in the set from 0 to the square root of a over 2 pi. Now we just want to make sure in the end that if we find critical points of this function, that they are within the domain. And they should be, because it's a cubic, and then beyond square root of a over 2 pi, this thing just flares out to negative infinity. So we shouldn't have to worry about any critical points outside of the domain. However, it's always very good practice to identify your domain to make sure that when you do find critical points, you're not coming up with critical points that are not physical. So they're outside of the physical realm of physical possibilities. Okay, so we've done the modeling part. We have our domain, we have our function. We started off with pi r squared h. We used a constraint to eliminate the variable h, so we solved for h. I think I said r earlier, but I meant h. So now the volume is only a function of r, and here it is. So we just take the derivative. dv dr a over 2 minus 3 pi r squared. Now we took the derivative and we're looking for critical points, so we want to set the derivative equal to 0. So we set this equal to 0. And solving it, okay, so these are my mental steps. This minus this is equal to 0. I see that a lot. A minus b equals 0. Well, then a has to equal b. So a over this has to equal that, because if their difference is 0, this term equals that term. So in my mind, I just imagine changing this minus to an equals. I have a over 2 equals 3 pi r squared. Divide by the 3 pi, so we get a over 6 pi, and that's r squared, So r is going to equal plus or minus the square root of a over 6 pi. So the steps in detail, if you want to write them out, a over 2 equals 3 pi r squared, a over 6 pi equals r squared, and then take the square root and you obtain this. Of course, the negative root is outside of our domain, so we're not interested in that. We don't need a negative radius. So the critical point is at square root of a over 6 pi. So we'll call that r star is equal to the square root of a over 6 pi. And notice that this is less than the boundary point here, square root of a over 2 pi, because if we do a over 6 as opposed to a over 2, a over 6 will be a smaller number. Okay, so lastly, let's actually figure out what the maximum volume is. So to do that, we just have to substitute this formula for r star back into our volume equation. So we get v of r star, so we get a over 2. Now r star was the square root of a over 6 pi, and then minus pi r cubed. So we're going to get a over 6 pi to the 3 halves. So the square root is 1/2, and then we cube it to get 3 halves. Okay, well a times the square root of a is a to the 3 halves. We have a 1 over square root of pi here, and then over here we have pi over pi to the 3 halves. That's the same as a 1 over root pi. Because think about it, pi to the 1, pi to the 3 halves, we subtract. This whole quantity is equal to pi to the negative 1/2, or 1 over the square root of pi. So there's some common stuff going on. We have, so let's do, we have a to the 3 halves over square root of pi in both terms. And then we're still left with 1 over 2 square root of 6 minus 1 over 6 to the 3 halves. Now 6 to the 3 halves is the same as 6 square root of 6. Right, because 6 to the 3 halves is equal to 6 times 6 to the 1/2. So it's 6 square root of 6. Now notice I also have a common square root of 6. So it's a to the 3 halves divided by root 6 pi. And then we have 1/2 minus 1/6 left over. 1/2 minus 1/6. Well, 1/2 is equal to 3/6. 3/6 minus 1/6 is 2/6 or 1/3. So the whole thing is equal to a to the 3 halves over 3 square root of 6 pi. What a nice, simple formula. So you can see I didn't just stop at r star or just plug it in here. With a little bit of algebra, I have a very simple formula. So this is a general purpose formula. Whenever you are trying to construct a cylinder with a fixed amount of surface area, the maximum possible volume is whatever the amount of surface area is to the 3 halves divided by 3 square root of 6 pi. That's kind of a cool formula. So with 100 square inches of sheet metal, 100 to the 3 halves is 1,000. That makes sense because the square root of 100 is 10, and 10 cubed is 1,000. So we get 1,000 over 3 over 6 square root over pi square root. So with 100 square inches of aluminum, you can the maximum size cylindrical can you can construct has a volume of 76.7764776. So that's 76.7764776. Okay, I have a cool number. Cubic inches. So with 100 square inches of aluminum, you can construct a can that can hold 76.776 cubic inches of water or paint or whatever you want. So that's just one example. Any other, if someone says, okay, well, what happens if the total area is 150? Okay, you can plug 150 in here and you get, what's the volume, maximum volume you can construct with 150 square inches of aluminum, and so forth. So one formula that solves kind of an entire class of problems with one single swoop.